Section 4.5, integration by substitution. Do you remember back when we did derivatives, not so long ago, back in chapter 3? We had some rules for derivatives. We had the chain rule, the product rule, and the quotient rule. And when we did those rules, I told you these are the most important things when it comes to derivatives. If you cannot use the chain rule, the product rule, the quotient rule, you cannot do derivatives. This is the equivalent for integrals. Integration by substitution. Okay? This is, for the remainder of this course, this is the single most important section. Because if you cannot do integration by substitution, you cannot do anything that we're going to talk about from here on in. And when you take Calc 2 next semester, you will use integration by substitution almost daily. You will learn other techniques for integration also, but I absolutely promise you will use integration by substitution almost all the time. Here's the idea behind integration by substitution. If I were to ask you to compute the antiderivative of 2x times x squared plus 5 dx, could you do it? What's that? Not right now. Yes, you could. How would you do it? You could take the x squared plus 5 and you could FOIL it out, and then you could distribute the 2x through, and then you could do it term by term, correctly? Correct? Easy to do? Not so bad. Right? What if I change that to a 20? Can you find the antiderivative? Well, in theory, yes, I can. In theory, I could FOIL that thing out 20 times. I'm not very convinced I would have the right answer. And then I could distribute the 2x through and I could integrate. This is the sort of problem we're going to learn how to answer. How come we can't just do the antiderivative of 2x and then do the antiderivative of x squared plus 5 to the 20? And then multiply our answers. Do we have a product rule for antiderivatives? No, unfortunately, we don't have a product rule for antiderivatives. Okay? So what we're going to learn is something called integration by substitution. Integration by substitution is really the reverse of the chain rule. And here's what I mean by that. If I asked you to take the derivative of f of g of x, what would you tell me to do? How do you take the derivative of a composition like that? Don't tell me you forgot the chain rule already. How's the chain rule work? You take the derivative of the outside. What do you do to the inside? Leave it alone. But then you need to multiply by derivative of the inside. There's our chain rule. Now what I'm going to do is I'm going to do an integral on both sides of that equation. So I'm going to have antiderivative of the derivative of f of g of x dx equals the antiderivative of f prime of g of x times g prime of x dx. What happens on the left-hand side? What's the antiderivative of a derivative? Well, it's not 1. It's whatever the function is, isn't it? Derivatives and antiderivatives are inverse operations. It's like adding 5 and then subtracting 5. If you add 5 and then subtract 5, what happens? You end up right back where you started. If you do derivative and do antiderivative, what happens? You end up almost right back where you started. So this should be f of g of x plus c, Correct? When we do antiderivatives, we always have a plus c. Equals the antiderivative of f prime of g of x times g prime of x dx. All right, and that's known as our, this here is known as our integration by substitution formula. But very rarely will we actually write it like that. Okay, so back to this problem that we didn't think we could do. Antiderivative of 2x times x squared plus 5 to the 20 dx. Look at what this integration by substitution formula has. Notice that inside of parentheses here we have a g of x, and then outside the parentheses we have the derivative of g of x. We had the same thing here. Inside the parentheses I have a function x squared plus 5. What do I have outside the parentheses? 2x. And how is 2x related to x squared plus 5? Nope. Derivative. Derivative is quite often still the right answer in this class. The derivative of x squared plus 5 gives me 2x. That's exactly what we have here. We have our x squared plus 5, that's our g of x, times the derivative of g of x. Okay, so here's why this is called integration by substitution. What we do is we make a substitution. We change our variables. I'm going to write u equals x squared plus 5. If I take the derivative, I would have du dx is, what's the derivative of x squared plus 5? 2x. So this is generally written this way. Generally I write du is 2x dx. I just moved the dx over. And you're going to get in the habit of doing that all in one step. Generally I would write right from the beginning, du is 2x dx. So here's what we do. We make substitutions. This becomes the integral of x squared plus 5. X squared plus 5 is u. X squared plus 5 is just u. So that part becomes u to the 20. And then what happens with 2x dx? 2x dx is exactly the same as du. So that's why this is called substitution. We substituted in a different letter. Instead of using the letter x, we decided to use u as x squared plus 5. That changes that to be just the integral of u to the 20 du. Can you find the antiderivative of u to the 20 du? Yes, what's the antiderivative of u to the 20 du? 1 over 21 u to the 21. So this becomes 1 over 21 u to the 21 plus c. And we're almost done. The last step is our original integral started with x's, so our answer should end with x's. So I'm not going to write u anymore. Instead of u, I'm going to write x squared plus 5. So my final answer would be 1 over 21 x squared plus 5 to the 21 plus c. Questions on that one? All right, well, this integration by substitution allows us to be able to find antiderivatives for a whole bunch of new problems. For example, I might have the antiderivative of 3x squared times cosine cubed dx, or cosine of x cubed dx. The first thing I notice in this problem has multiplication. When am I going to use u substitution? I'm going to use u substitution almost any time my antiderivative has multiplication or division involved. Why? Do we have a product rule or a quotient rule for antiderivatives? No, we only have those for derivatives. All right, so what we need to do is we need to make a substitution. The general idea is you want to let u equal something, and what should happen is when you take the derivative, you should get one of the other pieces you see. So any guesses on what u should be? Close. I don't think it should be cosine x cubed. I think it should just be x cubed. Why should it just be x cubed? What happens when I take the derivative of x cubed? I get this other piece that I see. I get just a 3x squared. If I were to let u be cosine of x cubed, in order to take the derivative, I'd have to use the chain rule, and I'd have negative sine of x cubed times 3x squared. I would see the 3x squared, but I wouldn't know what to do with all that sine stuff. So du is 3x squared dx. So this becomes integral of what? What do I have? What happens to all this stuff? What happens to the 3x squared and the dx? That becomes du. And this x cubed is u, so that's just cosine u. So you see how making the substitution made the multiplication go away. Now we can find the antiderivative. What's the antiderivative of cosine u? Negative sign? Positive sign? Positive sign? Not negative sign? Positive. You're positive? You're positive. Sine u plus c. And then again, our problem started with x's. Our problem should end with x's. Sine of x cubed plus c. Questions on that one? All right, so far I've purposely set up these problems so that when I take du, the du part perfectly matches with what's left out here. That won't always happen. What will happen is the x's will have to match. I'll have to get an x squared dx, but the numbers won't always match. So let me show you what you do when the numbers don't match. Let's say I had the antiderivative of x squared times the square root of x cubed plus 4 dx. All right, so I look at that problem, and immediately, right away, I think I should use u substitution. What right away immediately tells me that this problem is going to need u substitution? There's multiplication right there. Whenever there's multiplication, you're going to need u substitution. What should u be? U should be x cubed plus 4. Why should u be x cubed plus 4? Because you don't like it. Well, I suppose that's true, but I don't think that's a great reason. It's what's inside the square root. In general, your u is going to be the thing that's inside the parentheses. In this one, u was x cubed. It was inside the parentheses. I really should probably rewrite this one as x squared, x cubed plus 4 to the 1/2. In general, u is going to be the thing that's inside the parentheses. So I take the derivative. du is, what's the derivative of x cubed plus 4? 3x squared dx. All right, so that's going to become u. But I have a problem. Over here, I need 3x squared, but I don't have that here. Over here I have x squared and dx. I need 3x squared dx. I'm missing a 3. What do? Multiply by 3. I can just take an integral and multiply it by 3. Doesn't that change the answer? And also you divide by 3. That's exactly right. So there's what you do if your numbers don't match. If you need a 3x squared, put in a 3. Put the 3 there. That's okay. But if you're going to multiply by 3, you've got to balance it by dividing by 3. Or in this case, I chose to write it as multiply by a third. So that's what you do if your numbers don't match. If your numbers don't match, that's okay. Balance them out. If you need a 3, put in a 3, but balance it with a 1/3. All right, so this becomes 1/3. The antiderivative, u to the 1/2 du. The 3x squared dx, all that became my du. And this is u to the 1/2. That's going to be 1/3 times. What's the antiderivative of u to the 1/2? It's going to be u to the, what power? 3/2. Flip and multiply by 2/3. Plus c. Final answer, I put my x's back in. My final answer looks like 2/9 x cubed plus 4 to the 3/2 plus c. Questions on that one? How about the antiderivative of sine of 10x dx? I don't see multiplication this time, but I still look at that problem and I still say I really should use u substitution. What tells me I should use u substitution? The 10x inside of the sine. I know the antiderivative of sine x. I don't know the antiderivative of sine of anything else. The only thing I know is sine x. Can't have other things there. So, even though there's not multiplication, this is still a u substitution problem. U is 10x. So du is 10 dx. So I see exactly the same problem again as I had last time. I need a 10 dx. Right now, all I have outside is a dx. So I need to fix it. So I put a 10 in there. And the penalty for putting in a 10? Multiply by a 1/10. That's all. So now, that 10 and that dx, that's my du, and the 10x, that's my u. So this becomes 1/10 integral sine u du. What's the antiderivative of sine u? Negative cosine u? So that's negative 1/10 cosine u plus c. And again, my last step would be plug my x's back in. Negative 1/10 cosine 10x plus c. James?
Why doesn't it affect the problem by putting the 1/10 outside?
Why does it not affect the problem by putting the 1/10 outside the integral? Excellent question. Anybody got an answer? That's right. We had a rule back a few sections ago that if we had the integral of k f of x dx, we could write that as k times the integral of f of x dx.
And that's the same thing as splitting up.
That's the same thing as splitting it up. So if I put the 10 here and I put the 1/10 out there, if I wanted to, I could move the 1/10 back in, and 1/10 times 10 would be 1. So really what I'm doing is I'm multiplying by 1. I'm just writing 1 as a funny way. I'm writing it as 10 on the inside and 1/10 on the outside. That's all. Other questions? All right. Antiderivative of secant x, tan x, dx. Got some multiplication there. What do I do? Use u substitution. U is going to be? U will never be x. Because that doesn't really help you. If u is x, then this is just going to become secant u, tangent u, du. You really didn't do anything but changed all the x's to all the u's. U will never be the letter x. James? U is going to be tangent x. All right, good guess. U is going to be tangent x. So du is, what's the derivative of tangent x? Secant squared x. That's no good. Why is that no good? I can't balance it. I need a secant squared. I can multiply by secant, but can I divide by secant on the outside? No, you can only do that trick with numbers. You cannot do it with variables. So I don't think u equals tangent x is the right substitution. Because when I take the derivative, I get secant squared. I don't have a secant squared over here to balance with. Doesn't work out. Good guess, but that one wasn't right. Let u be secant. Okay. If u is secant x, then du is, what's the derivative of secant? Secant x, tangent x. I don't think that helps either, because u is going to be secant, so the secant one is going to be u. I would then need a secant tangent. Do I have another secant tangent? Oh, you can solve it.
Why are we doing that?
You do not need u substitution. This was a trick question. Just because you see multiplication does not mean you always need u substitution. What's the antiderivative of secant x tangent x? Secant x. U substitution is not needed for that problem. So be careful of that. Just because you see multiplication does not absolutely guarantee you will need u substitution. How often is that going to happen? Very, very rarely. If you see multiplication 99.9% of the time, you will need u substitution. All right, so that was a trick question. But here's an interesting thing. Let's try a slightly different problem. Now I did make that secant squared. So I have the integral of secant squared x, tangent x dx. You see multiplication. What should u be? Most people would say u should be tangent, because the derivative of tangent will give you secant squared. So you could let u be tangent x, and then du would be secant squared x dx. So this would become integral, what would I have? The tangent x becomes u, and the secant squared x dx becomes just du. What's the antiderivative of u du? One half u squared plus c. So I plug my tangent back in, I get 1/2 tangent squared x plus c. Now, what makes this problem interesting, I think, I'm going to do it again. Somebody might say, let u be secant x. Clever. That was really my only other choice, wasn't it? Either had to be tangent or secant. There's only two choices here. So du is, what's the derivative of secant x? Secant x, tan x, dx. So notice what happens. For secant squared, one of the secants becomes u, and then you have a secant tangent left over, don't you? In fact, I'm going to write this way. This is the integral of secant x times secant x times tangent x dx. So this secant becomes my u. And what about this secant tangent dx? That becomes du. So I get the same problem. I get the integral of u du, which is still 1/2 u squared plus c. But now my answer is 1/2 secant squared x plus c. So what's interesting about that problem? I did it two different ways and I got two different answers, right? This was answer number 1 and that was answer number 2. Are those the same? They're not?
Well,
Is-
it depends on what C is, right?
It depends on what C is. Very good. So, this C is different from that C. But what happens is, these two graphs must match up for some value of C. Let's take a calculator and graph those and see what they look like. Did I bring my calculator today? Did. Y equals 1/2 tangent, I'll write it this way, tangent x squared, and then 1/2 times 1 over cosine x squared. Did those turn out to be exactly the same? No, I don't think so. I think you could, if you watched carefully, you could see just a little bit. One graph is slightly just above the other. But what can you tell me about the two graphs? Yeah, we would call these parallel graphs. Now, normally we only talk about parallel when we talk about lines. But these are parallel. And what I really mean by parallel is they differ by just a constant. Let's see if we can look at our table here. Oops. Table set up. So, at 0 they differ by 0.5. At 1 they differ by. At 2 they differ by. So these are exactly the same two graphs. It's just that one of them is 0.5 higher than the other. So, if you call C 0 on this one, and I think if you call C 0.5 on that one, then they would be exactly the same graphs. So that's interesting. When you do antiderivatives, sometimes you can do antiderivatives, you can do them in different ways. And based on the way you do it, you may get answers that look very different. But what ends up happening is you have parallel graphs. They simply differ by the constant. By appropriately picking the value of C, the two graphs will be exactly the same. Questions on that? All right, now we're going to talk about what do you do with definite integrals? What's the difference? So far we've done a bunch of integrals. What's the difference between an integral and a definite integral? Those are terms you should be familiar with. This would be called an integral. What's a definite integral? Well, what other things have we done with integrals? What's that? Well, this would be called an indefinite integral. Ones that are in an interval are called definite integrals. So a definite integral would look something like the integral from 0 to 2 of, I don't know, what do you want? How about x plus 1 times x squared plus 2x plus 8 to the 6th dx. So what do you do when you have numbers like this? Well, the first thing you should do is you should look at that problem and you should say, I think I need to use U substitution. Why should you look at that problem and say, I think I need to use U substitution? There's certainly multiplication there, and you've got a fairly big power. If this were a power 2, well, I could FOIL it out if I wanted to, but with a power 6, I probably don't want to do that. All right, so I'm going to let U be something. What should U be? Why do you pick x squared plus 2x plus 8? Why not x plus 1? What's that? Exactly. Generally, what you want to do when you're deciding which one to pick U is generally going to be the one inside the parentheses, but it's generally going to be the one with the bigger powers. Because here I notice I have an x squared. When I take the derivative, I'm going to get an x. I'll be able to work that out, hopefully. Or the other reason I would pick U to be x squared plus 2x plus 8 is it's the one with the exponent on the outside also. That's a general good hint, too. So x squared plus 2x plus 8. So what's du? 2x plus 2 dx. Okay, so if I'm going to call x squared plus 2x plus 8u, then outside I need to have a 2x plus 2. Do I have a 2x plus 2 out here? I don't, but I can fix it, can't I? If I multiply by 2 right there, then I have a 2x plus 2. And the penalty for multiplying by 2? Divide by 2. Whoops, you can't see what I just did there. There it is. I multiplied by the 2, and I divided by the 2. So this becomes the integral of, what am I going to have in here? Just u to the 6th du, correct? Okay, good question. No. But there's something missing before I even get to that. Not the 2, but the 1/2 is still up front. Okay, when you change your letters, you also change your interval. So, notice these are x numbers. This is x goes from 0 to x goes to 2. But now I switched it so I'm using u's. So what I should do is I should take x equals 0 and plug it in right here. If x equals 0, then u is going to be 8. So my bottom number now becomes an 8. And then when x is 2, I plug 2 into here. When I plug 2 in, I get 4 plus 4 plus 8. 4 plus 4 plus 8 is 16. So when you do U substitution on a definite integral, not only do you change your letters, you also change your numbers. So watch out for that. That's something that a lot of people will forget to do. They'll forget to change their numbers. I find the antiderivative. The antiderivative is the 1/2 is still there. 1/7 u to the 7th. And then I'm using the numbers 8 and 16 now. So all I have to do is I plug in 16. So I'm going to write this as 1/14 times 16 to the 7th minus 1/14 times 8 to the 7th. And I'm just going to leave my answer like that. I'm not even going to bother typing that into my calculator because 16 to the 7th is going to be an awful big number. I'll just leave it like so. Questions on that one? All right, so notice what happens with a definite integral. When you change your letters, you also change your numbers, and then do you ever go back to your x's? No. Once you change your numbers, there's no need to go back to your x's. Could you go back to your x's if you wanted to? You could go back to your x's, but then what would you have to do? You have to change your numbers back too. It would be a lot of extra work. If you go back to x's, you plug the x's back in, that's fine, but then you got to change your numbers again. And then you got to go ahead and plug in the x numbers anyway. You might as well just change your numbers right from the beginning and then use those new numbers and plug them in. Saves you some work. All right, let's see. I need to come up with another good problem here. The integral from 0 to pi of sine of 3x cosine 3x dx. Once again, I see multiplication in my problem. Multiplication tells me I'm most likely going to need u substitution. What should u be? U could be cosine 3x, because if I take the derivative of cosine 3x, what am I going to get? I would get the negative sine 3x. I could make that work. Could u be sine 3x? Sure, because what's the derivative of sine 3x going to be? It's going to have a cosine 3x. So again, I think this is another problem where we have two choices which one we want to call u. I don't think it matters. If it doesn't matter, my personal preference would be, I'm going to let u be sine 3x. Why would I prefer to let u be sine instead of cosine? So I don't have to deal with the negative. The derivative of sine is positive cosine. If I let u be cosine, then derivative of cosine is going to be negative sine. It's going to be one more thing I got to remember. I got to have my minus sign everywhere. All right, so du would be, what's the derivative of sine 3x? Cosine 3x times 3 dx. Where did that times 3 come from? Chain rule. Don't forget your chain rule there. So I have almost what I need. I have a cosine 3x dx. I really need a 3 in here. So it's the same old trick. I'm going to stick a 3 in there. And if I stick a 3 in there, I need to put a 1/3 out there to balance it off. So we have 1/3. The integral sine 3x, that becomes u. And then everything else, 3 cosine 3x dx, that becomes du. But now I have to change my numbers. So I take x equals 0 and I plug it in over here. 3 times 0 is 0. And then I have sine of 0. What's sine of 0? 0. So that number didn't change. That's okay. That's a happy accident. That happens every now and then. And then I have to take pi and plug it in. 3 times pi is 3 pi. I need the sine of 3 pi. Sine of 3 pi is also 0. That makes this problem very easy. What's the answer? 0. I don't need to do any more work. And that will happen every once in a while. Every once in a while, when you do your u substitution, your bounds will match up, and then you're done. Makes it quite simple. Questions on that? All right, here's the last type of U substitution problem you're going to see. The antiderivative of x over x plus 2 to the fifth dx. We haven't done a lot of problems with fractions yet, but you will have fractions with problems with fractions. What should I do first? I don't think I want u to be x plus 2 to the fifth. I don't think I want it to be negative fifth either. Because, let's just write it down, if u is x plus 2 to the fifth, then the derivative would be 5 times x plus 2 to the fourth dx. If u is x plus 1 to the fifth, do I have x plus 2 to the fifth, do I have an x plus 2 to the fourth anywhere that I can use for my substitution? No. Very rarely do you want to let u be something with a parenthesis and a power on top of it. That's almost never going to work. I say almost never because, of course, I can rig one so that it did work. I don't think that's what you want to do. I think you just want u to be not x. U will never be x. U will be usually the thing inside the parentheses. U will be x plus 2. Usually. All right, but that leads to a problem. The problem is du is then what? 1 dx. So what's the problem? Well, u plus x plus 2, I can deal with that. That's just going to be u. Dx is going to be du. What do I do with that x right there? What's that? No. No. All right, so this is going to happen every now and then. Every now and then, you're going to let u be x plus 2. U is something linear. This will almost always happen when you have a linear term here. And in your original problem, you have an x up here that you can't get rid of, now using your du. So what you're going to do is you're going to take this little equation right here, and you're going to write x equals u minus 2. You're going to take that little linear equation, and you're going to solve it for x. So this becomes the antiderivative. I'm not going to write x. What am I going to write? U minus 2. Over, I'm not going to write x plus 2 to the fifth. I'm going to write u to the fifth. And I'm not going to write dx. I'm going to write du. Well, I still got division. Did that help very much? I can move the u up, so I can write this as the integral of u minus 2 times u to the negative 5 du. And then I can distribute. So this becomes the integral of u to the negative 4 minus 2 u to the negative 5 du. That's negative 1/3 u to the negative 3 plus 1/2 u to the negative 4 plus c. Add one to my powers, divide by my new powers. And finally, my problem started with x's. My problem should end with x's, not end with u's. So I plug my x's back in. This is going to be negative 1/3 x plus 2 to the negative 3 plus 1/2 x plus 2 to the negative 4 plus c. Questions on that one? All right, the last thing I want to do today, I want to talk about when U substitution doesn't work. Because what's going to happen right now, you're going to go and you're going to do your homework out of the book, or you're going to do that take-home quiz that I gave you, and U substitution is going to work on every single one of those problems. But the reality is U substitution doesn't work on everything. So I don't want you to get in the habit of thinking U substitution will always work. So let me give you an example where U substitution will not work. Antiderivative of the square root of x squared plus 1. U substitution will not work on that problem. Why not? Well, no, your only choice is U should be x squared plus 1. That's the thing inside the parentheses. But if U is going to be that, then du would be 2x dx. And what's the problem? How come U substitution will not work? I don't have an x outside, do I? I can fix the 2. Numbers we can always fix. If I don't have a 2, I can put a 2 there. I can't fix letters, though. I can't just add an x. I can't just multiply by an x and then divide by a 1 over x out here. That doesn't work. That rule with integrals only works putting numbers inside and out. It doesn't work with variables. So U substitution on this problem would not work. Okay? When else would U substitution not work? Well, a lot of times it doesn't work. Whenever your exponents aren't going to match up. Let's say I had, U substitution would still not work. How come U substitution would still not work? Because if I let U equal x squared plus 1, my du is going to be a 2x dx. I need an x squared on the outside. I don't have an x squared on the outside. I only have a 2x. So in order for U substitution to work for this problem, what's going to happen? What do I need out here instead of the x squared? Just I don't want an x squared. I want just an x. If I had an x out here, it would work. I can fix the 2. So the only way U substitution is going to work on this problem, if I have x squared plus 1 in here, I have to have an x out there. Now, these 2 problems that I've written down, they can be answered. And when you take Calc 2, you will learn a whole bunch of other techniques of integration. Both of these problems can be answered using a method called trigonometric substitution, which is very, very similar to U substitution, except it's called trigonometric substitution because it involves trigonometry. You substitute trigonometric functions in, and then it works out. Okay? But even after everything you learn in Calc 2, you learn about 6 or 7 different other ways to find antiderivatives. There are still lots of problems for which you cannot find antiderivatives. Antiderivatives are much more difficult than derivatives. You can find the derivative of almost anything at this point. Lots of things you cannot find the antiderivative for. Any questions?